To design a RC framed structure, performance-based design, and this is the grid layout. So you have in your plan view, it's a 2-bay grid and a 3-bay grid in the long and the short direction, 6 meters wide and 5 meters in this direction. And let's assume it's a 10-story building. I'm not going to draw all the 10 stories here. The main thing is the height of the ground floor is 4 meters. All the other ones are 3.5 meters. There are 10 stories. A few other things given, which is your seismic weight of the roof. And for floors, I believe it's L11. So who can find me the mass of floor and roof respectively? What's the mass of the roof?
The blower into area.
Yeah, how much is it? 80. And that's the weight of the roof, not the mass. And the weight of the floor is? So we can also do it in Excel. So if you look at your screens over there, so your weight of the floor is your area, which is 6 plus 6 plus 6, 18, times 5 plus 5, which is 10. So 18 times 10 times 11, because our roof loading is, floor loading is 11 kilonewton per meter square. So that's 1980 kilonewtons. Weight of roof, as he said, is 18 times 10 times 6 is 1080 kilonewtons. And then how do you convert that into mass? Divide or multiply? Multiply. So your corresponding mass is, if you look up here at the formula, would be this times 9.81, and that'll give you your corresponding mass. So at least now you have the mass of the floor and the roof figured out, right? And a few other parameters which is given. One is your design drift, which is, let's say you're designing for life safety, you want a design drift of 2.2%, so your Ddbd is 0.022 radians. The height of the ground floor is 4 meters, as we drew over there. Height for each story is 3.5 meters. The steel used in rebar is 500 megapascal yield strength. So how do you find yield strain? Multiply or divide? So that would be Fy over Es. Does anybody know what's Es? 200,000. So this is that's your strain. What are the units of strain? Less. Right? So these are your input parameters. Your height of the beam, let's assume, is, or it's given that because of plan geometry and the side geometry, we'll use 600 millimeters. So you can build an Excel spreadsheet that will make your life much more easier, as you have your inputs, so you can create a column of inputs, which is your theta D, Hg, height of each floor, Fy of steel, your E of steel, which is modulus of elasticity, that's 200,000 megapascal. Your height of beam is given, your total height of the building is 35.5, that you can calculate 9 stories of 3.5 meters, and then the last story is 4 meters. Well, you'll see that in the table pretty soon. Now you have to calculate, you have to convert this into an equal and single degree of freedom system, right? So for that, the best way would be to build a table like this, right? You have your story height. You have your story height. Start from story 1, which is your 4-meter height, and then just add 3.5, which is your story height to the subsequent column above. So you can start here and put 4, and then this could be the previous row plus 3.5, and so on. So here, if you see where it's referencing, right, which is right here, which is a story height. So previous row plus 3.5 here. You all know the dollar sign? Okay. So 35.5 is your total height. That's a check that your arithmetic is right. Right? And then Mi is the mass of each story. Your Mi you just calculated. It's 201834 or 201835 for each floor. Use 201835. It's the same for every floor except for the roof, which is, again, you can input it from here, which is 110092 kilos, right? So which is the critical story? Ground floor. Why? Tallest, which is 4 meters. So your HSC is 4 meters, right? and your phi critical, you'll calculate that. So what is phi? Do you recall the formula for phi from last night? So your phi I is 4/3 hi over h, 1 in the parenthesis 1 minus 0.25 hi over h. So you input that in your columns here. So if you look up here, it's 4/3 times hi, which is this, over the total height, which is 35.5. Again, that's a stagnant reference here with the dollar sign. Multiplied by 1 in the bracket 1 minus 0.25, again hi over h, and that is your shape function for that story. And then you can just drag it or copy paste it. It'll get you to the shape function for all the stories. A check that you should always do is the shape function for the loop should always be 1. So that is a check. So now you have HSC, which is your height of the critical story, which is 4 meters. You have phi C, which is equal to phi 1, which is 0.146. So what do we need to calculate? Delta I or delta C. Delta C is theta d times HSC. Is your design drift times your critical height, which would be 0.022 times 4, which is 0.088. Again, you can simplify your life by doing it in Excel. So that's delta D, which is our design input, our design drift times our height of the critical story, which is 4. And then delta I is phi I times delta C over phi C. So now you come back to your table here. Your next column is delta I. You populate that using this formula over here. So that would be delta I would be delta I is your phi I, which is your this column, G column, times delta C, which is up here, over phi C, which is up here. Right? These two are constant for a system. delta I, phi I is changing, everything else should be your stagnant reference. Does that make sense? Then you can pretty much drag and drop, and you can get all the columns populated, all the rows populated here. That'll give you delta I. So now you have Mi, delta I, and Hi, right? And if you look at your formulas for look at your formulas for delta D, Me, and He, your equivalent height, equivalent displacement, equivalent mass for the S-stop system, and those are the only things that we need. So now you calculate Mi delta I. That's a simple multiplication of Mi so it's Mi times delta I, right? And you populate that for all rows. And you do Mi times delta I square. You can do Mi delta I times delta I, or you can just triple multiply, up to you. And then Mi delta I Hi, right here, which is a product of Hi, Mi, delta I. I'll give you a minute if you want to build your spreadsheets right now, up to you. But you can also do the same thing in math software like MathCAD or SMath. SMath is free to use, free to download and use, that you can. Let me know if you're stuck anywhere, I can come help. Pi I is here.
एक जगह एच का बना देते हैं तो जब देते हैं 35 तो लाइक 25
कैसा चल रहा है?
अच्छा मैं समझ गई फंक्शन को पेश किया सबका तो नीचे शिफ्ट हो गई एट वाले खाते में शिफ्ट के साथ
Following so far?
इसको करता नहीं या फिर इसको कांस्टेंट करने के लिए टर्म
फाइसी की वैल्यू है फाइसी की वैल्यू
0.146
डेल्टा आई का फॉर्मूला क्या था
आई
It's on the board also, delta I.
जबकि इसका आंसर यही गलत है
Anybody needs troubleshooting? So once you build the table, can you calculate these three for me, please?
ठीक है इसका सम करो
Let me go one step forward and you can still keep on building your spreadsheets. So once you get mi delta I square, mi delta I hi. Take the summation of all these three columns, right? So just use the sum function in Excel. You need the summation of mi delta I, summation of mi delta I square, and summation of mi delta I hi. And once you have these three, if you look at the formulas here, essentially you have pretty much everything to get your S-top system properties, right? So your ME is
2.327.
ME is 1603760 kilograms, and that is you essentially is F26 divided by K15. So if you look up where F26 is, well, okay, you can start with delta D first, either way. So delta D is G26 divided by F26. So summation of this column divided by summation of the F column. So mi delta I square over mi delta I, summation of that. That gives you delta D, which is 0.43 meters. And ME summation of mi delta I divided by delta D, and HE is summation of mi delta I hi divided by summation of mi delta I. Clear so far? Were you able to follow the spreadsheet? Getting the same numbers? More or less. So now we have these three. What are our next steps? We need to find the ductility factor, right? And for that, what do we assume? Or what do we need to find? Sorry, what was that? Other way around. Delta Y by delta U. No, delta D by delta U. I'm just trying to confuse you. Which one it is?
Delta D by delta.
Yes, you're right. Because ductility cannot be less than 1, right? So mu is delta D over delta Y. We know this from, so delta E is equal to delta D. And do we know this yet?
Strain in the. Yes.
So Priestley gave us a formula when he was designing his system was theta YF is 0.5 LB over HB. What is our LB? You're analyzing the long direction. What is your LB? 6 meters.
6 meters.
What is your HB? HB is 600 millimeters. So let's calculate theta YF. Y, we have it over there. We calculated it previously. LB is 6 meters, right? So 6,000 millimeters. 600. Which is 0.0125. If you look up your Excel sheet or look up screen, it's already calculated over there, 0.0125. So your delta Y is theta YF times HE, which is this number, times HE, which is this number. So HE is 23.32 meters. One two five times 23.32. Which comes out to be 0.292 meters. Again, calculated using Excel over here. Falling so far? Want me to go slow? Ductility. So mu is ductility, which is delta D, which is right here, divided by delta Y, which is right here. So your mu is 1.474, which is right. And a good check is mu should be greater than 1 for your system to work, and this is greater than 1, so that's okay. What's next? Next is you have to calculate equivalent damping. Because you need to use the displacement spectra. You recall yesterday's notes, equivalent damping is
5 plus 120.
5 plus 120 times 1 over 1, 1 minus 1 over mu over pi. And if you, the only number you need from a calculation is mu, which you just calculated as 1.474. You plug that in this equation. Again, the formula is already feeded up here. And you get equivalent damping of 11.73. So, just, yeah, if you want to refer to the formula, you can just check it one time, but that should be correct. You get 11.73. Which is okay, high, low, what do you think? Well, a damping of 11.73. Now, one thing I should have specified that soil type for this site, and let's say it's Eurocode soil type B and a 0.35 or a 0.4 G spectra. The displacement spectra is already available in multiple literature, or you can create one for this damping ratio or this equivalent damping of 11.73, roughly 12. You know your delta D, you have to find from displacement spectra is your time period of the building itself. Is this visible to everybody? Okay, so you have spectral, come on. So you have spectral displacement on your y-axis, your time period on your x-axis, and these different curves represent different equivalent viscous damping for the system. It starts from 5%, goes all the way to 15.7, or all the way to 35. Ours is 11.73, so it should be somewhere in the middle of 10 and 15. What's your displacement? 0.43. So use the 0.43 line, which is drawn in blue, and just maybe extrapolate between 10 and 15 equivalent damping lines. So roughly over here, and probably it's bang in the middle of 2.5 and 3. So give it, time period is, what I took out from that is 2.75 seconds. Does that make sense? From the displacement spectra. Anybody want to dispute that? Everybody happy with 2.75? So your KE, if you're happy with 2.75, ME over so your KE then becomes this. It's 4 pi square ME over TE. Your ME was 1603760 kilos. So you can again use Excel for the calculation. Nobody caught this? KE is 4 pi square AB over TE square. Okay, and you put in the formula here, and you get this number. To take care of the units, it's kilonewton per meter.
Square.
TE square.
Once you have KE, your VB is KE times delta D. You have your delta D is 0.430 meters. KE is right up here. The product of the two, delta D and KE, will give you VB, which is your base shear, corresponding to a 2.2% drift. Converging on this number?
Yes. Somewhat the same.
Now what is the next step? Distribute this over the entire length of the entire height of the building.
N less than equal to.
So Fi, how do you distribute it?
VB into MI delta I over.
VB into
MI delta I over summation of MI.
my delta I. Yep. So Fi, because it's the story height is less than or equal to 10, is VB times MI delta I over summation of MI delta I. You know this, you calculated it, you know this from the table, you know this from the table. You can put in the formula in the columns itself for Fi. So you know VB, which will be a constant for this system at this moment. And then you have MI delta I for that story divided by the summation of MI delta I. Make sense? So now when you do it for all the 10 stories, do remember to sum them all together. And that's a check. Your VB, your summation of Fi along all stories should be equal to your VB. So this and the VB number should match. All converging on the same VB and the same division of forces. If it's a little bit off, that's okay. It's mostly approximate. So now you have your Fi for each story. You'll have your dead load, live load, plus minus Fi, that's your load combination. And then you use expected values for your design, expected values of your material resistance for your design, and you design just like basic principles of design. Following everybody? So, we did this for this direction, but this building has two directions, right? So you have, we did this for long direction. There's also a short direction. What I want you to do, and maybe you can work in groups of 4, is try doing this. You have the spreadsheet now, hopefully. You might have to change a few numbers here and there. Try doing this for the smaller direction. And the height of the beam, keep the height of the beam same.
We have different length in corresponding directions. Like in X direction, we have different length of beams. In this example, we have only 6 meters.
Oh, in X direction, you have different beams and different bays.
Yes, sir.
Yeah, you analyze for all the cases and then just use which one's the more conservative. So what will change for short direction? Is the length of the beam the only thing that's changing? So does that do anything to your S-stop system? Your YF changes, but nothing else changes, right? So you'll be probably looking at a different line on the displacement spectra for your TE. Your forces will change. So let's see what you find out in terms of your TE for the short direction and your forces. Just the total base shear should be fine. Theta YF, let's say theta YF short will change. Your corresponding ductility will change, Xi will change, and your VD will, time period will change. KE will change as well. And your VD. What did you get for theta YF?
0.0104.
10104. So your delta Y will be
0.243.
Then your ductility,
Mu 1.768.
1.768, which is your 0.43 divided by 0.243, right?
And damping
This guy, equivalent viscous damping,
14.48.
so it increased. 13.48. Just for convenience, you don't have a 14.48, you can probably use, it's closer to 15, just use the 15% equals damping. So your delta D is the same, right? And you go to 15, which is this line over here. Then you right there.
2.9.
9. Okay,
72376.
some big number. And then VB.
310.
3, 1.
979.69.
Okay.
Huh?
E, something.
154. Capital 3. 154. अरे ME बता रही हूँ, not MI. MI is something like 180.
Are you getting the same number for K equivalent? Then why is the VB different?
हाँ मास डिफरेंट है सर का फ्लोर और रूफ का हमारा
Time. Okay. So was there a huge change in VB or not?
yes there is change some variation
It's reduced. But in practicality, you'll probably not be using the same depth of the beam also. The depth of the beam might vary. But you have to analyze both directions and then design accordingly. Any questions? Questions or no questions? Yes, sir. HE is your the equivalent height of a single degree of freedom system. So you're taking a multiple degree of freedom system, you're modeling it as a single degree of freedom system, and it will not have the same mass, it will not have the same height. So you're using an equivalent mass and an equivalent height of that single degree of freedom system to kind of simplify your analysis portion of the design. So that's what HE signifies. It's the equivalent height of the single degree of freedom system that's mimicked after the multiple degree of freedom system that the building itself is.
The mass suggests 2/3 of the ratio of, total height
No, it's done with, were you here yesterday? It has to be done by the summation of the moments and the summation of, first moment of inertia and the second moment of inertia. Alright. Other questions? So this was the easy one. Now we'll complicate things a little better because these kind of structures not really exist in practice. You generally have dual frames where you have a shear wall system and a concrete frame system. So we'll analyze that next. The analysis is pretty much similar. It's a little bit more math heavy and a bit more, I need to go over some concepts before we start that. So I would highly recommend you build this spreadsheet. You won't be using it for the dual system. We'll build a separate spreadsheet for that, but you'll use a lot of elements from here and the concepts, especially the table of mi delta I and all that. So I would say take some time to finish this and then head off for a break.